So yeah, so I'm not going to go through all these notes. Okay, I don't want to finish like all of these, but in looking at these, right, and maybe watching the video, or in looking at the completed notes that I also post online there on our Schoology page. Did anyone have any one of these that you want me to go over? Any questions about any of these examples? You have some more examples with taking the derivative of the logarithm. Here they want you to use logarithm properties and then differentiate, right? And then here's one writing the equation of a tangent line using this. By the way, in example 8, right, this would well, actually, I don't know. I was going to say it's going to be a graphing calculator, but I don't think it necessarily has to be. Never mind. Yeah, never mind. It doesn't need to be a graphing calculator necessarily. Okay, and then there's like another little like AP question, right? Multiple choice. That would be like an AP style question you might see. Okay, and then finally there's the derivative here for bases other than e, right? So if you want to take the derivative of a to the x, where a is not necessarily the base e, right? Then it's a to the x again times the natural log of a, and there's the chain rule version of it. And then there were 2 practice examples there with a product rule one right here, right? So keep an eye out, for that. That was a product rule. So does anyone want me to go over any one of these? Any questions on any of these? We're all okay. We got to watch the video and stuff like that. Okay, I'll take your silence as we're okay then. And if not, again, please reach out, ask me some questions, all right? But again, this is taken care of in the video that I posted, and it was taken care of in the completed notes, so you can see both of those things, okay? But if you have more questions, please, please, please let me know, one way or the other. Sign up for office hours or what have you. All right, then, if there's no questions on that, let's take a look at this quiz review. So today, then, we will have a quiz released. After this class, I will release the quiz, okay, where it's going to be mostly derivative rule practice. Okay, so chain rule mostly, but you could see some quotient and product rule stuff thrown in. And of course, the power rule will be there as well, right? Because, power rule is one of the basic derivative operations that we have. Procedures that we have, I guess I should say. Okay, and then 3.3, right? That was like your position, velocity, acceleration kind of stuff too. Okay, so you're going to see position, velocity, acceleration questions and derivatives. On the quiz, there will be some choice about what questions you get to do. Okay, so like you're going to have like, I think there's like 10 derivatives and you have to pick 8, or there's 8 derivatives and you have to pick 6 or something like that. Okay, you won't get any credit for doing extra, so don't think you're gonna just like get them all done and then you're gonna have me just go around and pick which ones I'm gonna grade. You need to identify which ones you want me to grade. If you try all of them, that's fine, but I won't if you don't indicate to me which ones you want me to grade, then I'm going to just pick the first group of them or whatever and say that's them. Okay, so please indicate which ones you want me to grade when you do your quiz, and that will be due on Monday, okay, along with your homework for this week. And there is a homework assignment for today too, in addition to the review. Okay, we'll work on the review. In addition to the review, so you can see here some of the questions, right? All right, and here's the equation for a tangent line, and here you can see here's a particle motion kind of question. So again, stuff you might expect to see on your quiz, right? If you then scroll further down, you'll see the worked out answers right here, okay, with some brief explanations and stuff like that too. So you can feel free, to use all of this to guide you, okay? So, if you are feeling good and you don't want to stick around, you're like, Mr. Wade, you know what, I think I can do this. I'm going to go ahead and just, use the answer key to help me learn this. You don't have to stick around if you don't want to for the rest of this class, okay? I'm going to be going over this. Everyone else that wants to stick around and ask questions or just go through these, I'm happy to do that too, and I will be happy to do it for the remaining time in class. That means even beyond like the the 60-minute face-to-face time that I'm allowed to have for you guys, whatever. So your choice. Whatever you want to do. If you're ready to go, then see you. That's great. But if you want to stick around and go through this, great. And I would encourage you to stick around too, because chain rule is one of the harder things. So this, by the way, this document, this PDF, is available on our Schoology site right now, right? So if you go to the updates page and you click on the homework key quiz review lessons video link there, okay, then you will be able to find the PDF and stuff like that too, okay? But of course, you can also just follow along with me here. So, all right. Well, looking at this document, does anyone have any preference about which one I start at? I could start at number 1 if you want me to and just kind of work my way through, or if there's any of them in particular you want me to look at, first before we, I'm happy to just jump around too if you want. So, but speak up. What do you guys want? I'll go with whoever speaks first. Let's do that. Okay. Number 5. You got it. Ooh, number 5. Okay. Yep. So if you go to our updates page on Schoology, okay, that most recent post that I made, Charlie, if you click on the first link in that update, it should say like quiz review on it there, and that's where the PDF will be. Did you find it okay? Okay. So yeah, so that's where the document is. Okay. And of course, if you guys, obviously I should have really released this yesterday to you guys, and I'm sorry I wasn't thinking ahead because some of you guys may like to print it out and stuff like that. But if nothing else, you can just write on a sheet of paper, and just number it 5 and say, okay, here's number 5 for the quiz review. Okay, so let's talk about number 5. So first of all, okay, I see a root, right? And anytime we see a root, what should we do with that root? Yeah, rewrite it, right? So this is a 4th root, and so I'm going to rewrite this as x minus 1. In fact, goodness gracious, I don't have enough room. Right, it's kind of small here. X minus 1 over 2x plus 7 to the 5th, and then to the 1/4, right? Because that whole quantity is to the 1/4. All right, so that 5th power is underneath the 4th. So we have this. But now, of course, when I have a power raised to another power like this, we can simplify that by multiplying the powers together, right? So I could really write this as to the 5/4. Okay, which maybe makes it a little bit more palatable than what we had before. Okay, so now just looking at what we've got, so now we've kind of rewritten it as much as we can. Now we're ready to actually take the derivative, right? Which is what our directions say up here. Find the derivative, right? And we'll just say this is I don't know, y equals here. Okay, so if I want to find the derivative here, if I want to find dy dx, okay, what kind of rules are we going to need to use here to find this derivative? What tools are we going to need to use to take this derivative? What rules? Okay, yep, chain rule, Sion, exactly right. Okay, we have an outer function and an inner function, right? And so let me see if I can lasso this thing here. Okay, our outer function is something to the 5/4 power, right? Something to the 5/4 power. And so we'll have to take the derivative of something to the 5/4. And then the inner thing, when I go to take the derivative of the blue, what's that going to need? What tool we need to use when I go to take the derivative of the thing in blue? Yeah, then a quotient rule, right? So in the process of doing a chain rule, we're going to have to then use a quotient rule, okay? So let's break it down here. So something to the 5/4 becomes 5/4 times, and I'll put this in blue, x minus 1 over 2x plus 7. And then we subtract 1 from that power, right? So it becomes 1/4. And then we multiply the derivative of what's inside. And by in taking the derivative of what's inside, that's going to require that quotient rule that Sophia was talking about. Okay? So it'll be the bottom times the derivative of the top minus the top times the derivative of the bottom. So thankfully the derivatives aren't too crazy for that quotient rule there. All over the bottom squared. Okay? And then at this point, you're done. We've taken the derivative, okay? You do not need to simplify this if you don't want to. You do not need to rewrite this if you don't want to, okay? We could rewrite it some, but I mean, this is the derivative. That's all we were asked to do. That's all you will be asked to do on the quiz. And so this, you can say, is your final answer if you like, right here. Okay? If we did want to simplify this, I'll just show you that because, it's sometimes helpful to see. Good gracious. All right, let me see if I can figure this out here. So that 1/4 exponent can distribute to both the numerator and denominator. So we would have something like 5x minus 1 to the 1/4 power over 4 2x plus 7 to the 1/4 power times, and I'll go ahead and simplify this numerator over here, 2. So it'll be 2x plus 7 minus, and then let's see, distribute the 2, so it'll be 2x minus 2. So it'll be minus 2x plus 2, because you also have to distribute that minus sign there too. Over 2x plus 7 squared. I can put a few more things together here, and so we have 5x minus 1 to the 1/4, and then 2x take away 2x, those are going to be gone, and then 7 plus 2 is 9, so well actually 9 times 5 would be 45. We can just make that all over, and then 4, and then these 2x plus 7s are the same base, right? So we can actually add their exponents there, and it becomes 2x plus 7 to, yeah, that's a squared, right? Yeah, it's a squared. So 9/4, like that. So it does kind of simplify together a little bit nicely, right? Not too shabby right there. If you want to simplify it, but you do not need to, right? On the quiz, you'll just need to take the derivative, and that's it. So you don't have to simplify it. But realize that you can, and you should be able to simplify it down if called upon to do so. Okay, number 5, there it is. Questions on any of that? Good to go? All right. Sam, did you, by the way, get my message to you yesterday from your homework submission? Okay, yep, no worries. Yeah, great. All right, next question. What would you like to see? Number 2. Okay, number 2. Great. So, looking at this, right, what rules do we see that we'll need to use here? Quotient, okay. What else? Chain. Yeah, quotient and chain rule here. Do we need to use the quotient rule, though? I can rewrite this, can't I? How can I rewrite this so I don't need a quotient rule anymore? Yes, yes. Make that divide by 7 become a 1/7. Now, all that is just a coefficient. So in other words, we can kind of like ignore it. And so what was a quotient rule now becomes really just this was a quotient rule and a chain rule. Now it just becomes a chain rule. That's all we have to worry about here. That 4, so again, let me do the outer and the inner stuff here. All right, there. Oops. Well, didn't quite lasso the 2, but anyway. Let me try one more time. No one will be seated when they watch Mr. Wid lasso math. There we go. Okay. So there's our layers, right? 1/7 parentheses to the 4th, 1/7 of something to the 4th, and then something inside that we're going to multiply by the derivative of. So we just bring that 4 out front. Okay, to the 3rd, and we multiply by the derivative of what's inside. So, and there we go. Now, would John be wrong if he did the quotient rule here? Absolutely not. John, you absolutely could do the quotient rule there. It would work. It would be a little bit, messier, of course. I'll show that up here maybe or something like that. So it would be the bottom, 7, times the derivative of the top. So the derivative of the top would be 4 times 2x to the 3rd minus 6x plus 5 to the 3rd. And then times the derivative of what's inside, again, by the chain rule. So it would be 6x minus 6 minus the top, 2x to the 3rd minus 6x plus 5 to the 4th, times the derivative of the bottom. What's the derivative of 7? 0. So this whole piece goes away. All over the bottom squared. So 7 squared, like that. Okay, and lo and behold, right, if I cancel this 7 with one of these 7s here, right, and I now have 4/7, so there's the 4/7, 2x cubed minus 6x plus 5 to the 3rd, 2x cubed minus 6x plus 5 to the 3rd, times 6x minus 6, times 6x minus 6. So you see you get the same thing. And it's really not that much different, much harder work to do. So, questions on? So the chain rule, right, John, since we're taking the derivative of something to the 4th power, right, it's 4 times that something to the 3rd, then we multiply by the derivative of what's inside. And the derivative of 2x cubed minus 6x plus 5, whoops, it should be 6x squared, my bad. Mr. Wid. There you go, sorry. 6x squared minus 6. Okay, sorry, yes, that's the correct derivative of what's inside. All right. That's just the derivative of what's inside. All right. Next, other questions. Number 3, Joy? Oh, 8? Sorry, your microphone's really quiet. Okay, number 8. So what does this mean when it says find d squared y over dx squared? What does that mean that they're asking us to find here? The second derivative, right? So that means we have to take the derivative once and then take the derivative of that derivative, right? So dy dx, okay, becomes, well, the derivative of 5x is 5. The derivative of e to the 3x squared, all right, is e to the 3x squared times 6x, right? Again, this is the derivative of e to the something is e to that something, but then you multiply by the derivative of what was inside. So what's inside the e, right? The inside the e is what's in the power of the e there, right there. And so the derivative of that becomes 6x. Okay? So far, so good? So now we'll take the derivative again. And the reason why we get this like kind of weird notation is, so, right, we're taking the derivative of y with respect to x. And so in that process, right, the y comes up here in the numerator, and that's where we get the dy dx. But then if we do the derivative twice, okay, this is like doing the derivative twice here using that notation. Okay, we have two d's, right, so that's where we get the d squared from. And then dx times dx becomes dx squared, like that, of the y. And again, the y then just comes up in the numerator. So that's why we get that kind of notation indicating this is the second derivative, okay, because it's the d dx twice, right? And so that becomes d squared y over dx squared there. All right, anyway. Let's go take the second derivative. Okay, derivative of 5. Zero. Very good, Gavin. Yes. Okay. What about this derivative? What do I need to do now to take this derivative that I've circled right here? What rule do we need to use here? Or rules, I should say. Yes, Sion, a product. We did not have a product in our first derivative, right? This first derivative, there was no product rule that we need to use here. But in the second derivative, but within that first derivative, right, to then take the second derivative, right, take the derivative again, we have this product now of two functions. So be on your toes for that. Very common student mistake or cause of confusion here. We start with something that was not a product rule, right? We take its derivative using the chain rule, but in the process of that taking the derivative there, we create a product. And now when we go to take the derivative again, we have to use the product rule. And then within that product rule, we still have to take the derivative of e to the 3x squared again, so we're going to have another chain rule within that as well. Okay, so I'm going to put some parentheses in here so I don't have to worry about my minus sign and stuff like that. So again, it'll be the first times the derivative of the second plus the second times the derivative of the first, which is exactly what we had right there. So it's going to become the e to the 3x squared times 6x again. Okay, and so again, there's our second derivative. You could stop there. If you really want to simplify it, you can. So let's see here. I can factor out. I'll factor out like a negative e to the 3x squared and a 6, actually. And so we're left with 1 plus 6x squared, like that. Okay, so if you want to factor it out, you can. Not necessary though. Okay, this is a perfectly fine answer as well. All right. Does that make sense for you, Joy? Questions on any of that? Mm-hmm. Exactly. So first of all, we recognize, right, this is a product rule. And in the process of doing the product rule, right, we do the, I do the first thing, right, times the derivative of the second thing. So there's the first thing, and there's the derivative of that second thing, right? Then we add the second function times the derivative of the first function. So there's that second function. And then the derivative of this first function is going to be e to the 3x squared, right? Because the derivative of e to the something is e to the something again. but then times the derivative of what that something is. And that something is 3x squared, so its derivative becomes the 6x. That's why the other 6x shows up there. Okay, just like in the previous derivative that we took, right? E to the 3x squared, its derivative, right, which is what we're doing again, is e to the 3x squared times 6x. So it shows up twice. All right. Other questions. What else would you like to see done? Number 7. All right, the other second derivative. You got it. All right, I realize that I'm doing more of the talking here, so I should let you guys like jump in and say stuff too. All right. So cosecant of x, right? So what is the derivative of the cosecant of x? Yeah, negative cosecant times cotangent of x. Negative cosecant of x times cotangent of x, yeah. Okay, if there was something inside here, I want to say like a little thing, right? So if this were like cosecant of 2x, for example, now we're talking and using the chain rule. Okay, the derivative of the cosecant of 2x would be, I'll just use like y prime here, would be negative cosecant 2x cotangent 2x. So both of those keep just a plain old 2x inside of them, right? We don't take the derivative yet, but then we multiply by the derivative of that inside function 2. Even though that 2x shows up twice, right? The inside function was just 2x, so we multiply by its derivative, which is just 2. Okay? So that would be the derivative there if we had something inside that cosecant. All right? Or if you want a more general one, you say like cosecant of u, and then y prime would be negative cosecant u times the cotangent of u times, and then u prime, whatever the derivative of that u is, with respect to x or t or whatever the variables happen to be. All right, sorry, little side note, the tangential, we're not done yet. We have to take the derivative again, right? So d squared y over dx squared. Now when we go to take the derivative, what rule do we have to use? Product rule, exactly right, okay, because we have cosecant times cotangent, or negative cosecant times cotangent. Okay, and there's, we'll say our first, there's our second. So it's the first times the derivative of the second. And what's the derivative of cotangent? What is the derivative of cotangent of x? Yes, negative cosecant squared x. Okay, plus the second, so cotangent x, times the derivative of the first. And what is the derivative of, well, we already did it, I guess. Move this over here somewhere. The derivative of negative cosecant would be positive then, cosecant x, cotangent x. Negative cosecant x, then the derivative is negative cosecant cotangent, but it's already negative, so the negatives cancel out and we get that. All right, and so we could simplify here and say, okay, this is positive cosecant cubed of x plus cotangent squared x cosecant of x. We had a question similar to this in your homework too, I think, except it was with secant of x, I want to say, instead of cosecant of x. Okay. I guess I should exit Steam. We don't need to see that stuff. Okay, there we go. Any other questions? What else would you like me to do? Or what else would you like to do here? Exactly. Addition and multiplication are commutative, so you can totally do it the opposite direction where you do the derivative of the second times the first plus the derivative of the first times the second. Okay, so yeah, you can flip the order around there. That's fine. So basically, it's like you just want to make sure that you know, the first function, you multiply by the derivative of the second function, and then you add, and then you want to take the second function's derivative and multiply by the first function kind of thing. So, yeah. Some people will like refer to these as like f and g, and so then you just want to do like So you want to make sure that these two get multiplied together and these two get multiplied together. And you add the results. Okay. So, sorry, other questions? 11? Okay, yes, absolutely. So in this one, yeah, it looks like the directions are still just to take the derivative here, I think. Find the derivative of the following. So I think we're supposed to find the derivative, okay? So there's two paths we could take here that I can see, okay? Gosh, I don't know. Well, yeah. What would be our next step here? Ideas about taking the derivative of this thing, of this function here. How would we take this derivative? What should we do, right? I see a natural log right there, so what can we do? Ah, so Sarah comes in to save the day. Yes, because that would be the easier way, in my opinion, to go here, okay? Is it the only way to do it? No. You can absolutely take the derivative as it's currently written, and we'll do that here, but I'll show you what Sarah's talking about, right? So, Sarah, can you elaborate a little bit more? What property of logarithms do you specifically see that we could use here to help us out? Just what do you do, I guess, is what you could say, yeah. Yeah, exactly. Okay, a property of logarithms, right, is when you take when you take a log of a quotient, okay, you can change it to the log of the, gosh, is it the dividend minus the log of the divisor? I think that's what you'd say. Anyway, the log of the numerator minus the log of the denominator, okay, is what we can say too. Okay, and wow, does that make it a lot more simple when we break it up first using those log properties. Okay, so when I go to take the derivative of the natural log of something, right? What is the derivative of the natural log of something? What is the derivative of that? It's one we saw yesterday. Yeah, whatever's inside there. Yeah, I know, right? It's like, what do you say? Yeah, whatever the function, maybe you could say, yeah, or whatever the inside. So yeah, 1 over x cubed plus 1. But we're not done taking the derivative yet. What do I still have to do here at the end? Take the derivative of what's inside. That's right. So that would be 3x squared. And we'll do the same thing for this piece then. So 1, like Sophia said, 1 over what's inside there times the derivative of what's inside. Okay? And if you want to, again, you can put it all together and put your stuff in the numerator if you want to. But it's not necessary. You can absolutely stop right here and say, oh, I guess I should say this is like f prime of x. Okay, keep in mind this is still f of x, right? This is not a derivative. We use our properties of logarithms to simplify it to this point, and then we took the derivative here. Okay, so be careful with that. Sometimes students get kind of like mixed up, especially like a test scenario where they're like, oh, I did something, so that's the derivative. Nope, we just use simplifying. This is the derivative, or this. Okay, but there it is. If you want to simplify it. All right. Now, I said I would show you the other way, and I'll do that too. So I'm going to scoot this over here because you absolutely do not need to use the logarithm properties that Sarah recommended. Okay, it's not necessary here. We could like legitimately just do this as it's written. So what would that require? Well, you tell me. If I'm going to do this as it's currently written, what kind of rules are we going to need to use to take this derivative? What different like rules that we have are going to use to take this derivative as it's written? Okay, so eventually a quotient. What will be the first thing we need to do, though? Quotient will come eventually, but the first rule we'll have to use is what? We have a function inside of another function, so we have to use the chain rule. That's right. So it would be 1 over what's inside here. So it would be 1 over x cubed plus 1 over 2 minus x squared times then the derivative of what's inside, which will then be that quotient rule. So it would be bottom, so 2 minus x squared, times the derivative of the top, so 3x squared plus 1, the derivative of 1, 0, minus the top, x to the third plus 1, times the derivative of the bottom, so it would be negative 2x, all over the bottom squared. Okay, like that. Okay, so again, reviewing, right? Natural log of something, the derivative of the natural log of something is 1 over that something times the derivative of what's inside. So we're not taking the derivative of this thing, right? We're taking the derivative of what was inside. So that's why we didn't worry about that 1 for the numerator. So like that. It's this that's inside, that's what we take the derivative of. Okay, and so this does simplify not too terribly. Since we have 1 over this fraction, we can just do the reciprocal there. And let's see, you can also, simplify this around some. So it'd be like, what, 6x squared minus 3x to the fourth plus 2x to the fourth plus 2x, 2 minus x squared squared. So one of those squares, we cancel that 2 minus x squared there. And combine like terms, we'd have what? Negative x to the fourth plus 6x squared plus 2x all over x to the third plus 1 times 2 minus x squared. Woo. Okay, and these two things, this should be equivalent to that. Or that, if you like. Okay, and I can kind of buy it because we would need to get a common denominator here and here to be able to combine them together, and the common denominator would look like that. So, yeah, maybe. Okay, if I do my math correctly there. So, questions on that, or are we ready for another one? This, by the way, if you do this on the quiz, I will not dock you any points, right? If you don't do what Sarah suggested here and use your logarithm properties, right? If you just go for it like, brute force method, you can do it that way. And you can stop right here and say, Mr. Wade, there's my answer, and you're done. You don't need to do the simplification that I did right there. You are done right here. In fact, I would encourage you to stop, because the more simplification you do, the more possibility for error. And if you do an error in your simplification, then I may dock you a point. Okay? So you can absolutely do this if you want to, if a question like that shows up on the quiz. All right. Next. Number 10, yeah, sure, absolutely. All right, number 10. So let's see here. So number 10, okay, does not present any easy way to rewrite it, right? Okay, there is property for rewriting logarithms, but there's not really nice properties for rewriting like that. Okay, so we are kind of stuck with that a little bit. Same thing with sine, right? There's not really an easy way to rewrite sine of like 4x plus 3. So we'll just have to kind of, again, take the derivative of this thing. So let me see here if I can like give myself a little more space. I'm gonna like lasso this whole thing here. Yee, oh nuts! That was not a good lasso. Try again here. Like a calculus cowboy here. Lasso me some math problems. Move them on over. All right, here we go. So then number 10. We'll just take the derivative, right? So we have the derivative of e. And then we have the derivative of sine, right? And we can separate them because of this minus sign right here, right? You can keep them separate. So two separate things, and we'll just rejoin them with a subtraction. So what is the derivative of e to the something? E to that something again, right? So that's an easy one. Easiest derivative of my life. Okay, but then multiplied by the derivative of what's inside. So we have to multiply by this derivative. Okay, now we could have rewritten this as like x squared plus 1 to the negative 1. If you want to, that might make it a little bit easier here. As I currently have it written, I have to use a quotient rule. So it'll be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, and this is still not going to give me enough space. I'm going to move this over now too. Okay. So there's the derivative of e. All right, and then minus, so the derivative of sine is cosine. So we got cosine of 4x plus 3. Again, times the derivative of what's inside. What's the derivative of 4x plus 3? Just 4. That's right. There it is. Okay, and again, at this point, you could say, Mr. Witt, I'm done. I took the derivative. And you'd be right. And you can just circle your answer and say, no problem. There it is. And I give you full credit for that. Okay, of course, this does simplify some, you know, so we could say, all right, this is really like a e to the 1 over x squared plus 1. This would just cancel out because it's a 0 there. So we'd have negative 2x over x squared plus 1 quantity squared, and then minus 4 cosine 4x plus 3. That makes it a little bit prettier. Of course, if you chose to rewrite that e to the 1 over x squared plus 1, if you chose to rewrite that as x squared plus 1 to the negative 1, then the derivative looks slightly different. It would be like e to the x squared plus 1 to the negative 1 times negative x squared plus 1 to the negative 2 times 2x. We can see that right here is exactly that right here. Right? That simplifies to the exact same thing. So you can see you have that already. And then you do the same thing. And then the cosine would be the derivative of sine 4x plus 3 would be the same thing. It would still be the 4 cosine 4x plus 3. Okay. So again, just before I ask for the next question here, one thing I also want to point out, right, when it comes to taking these derivatives, right, the devil is in the details. So like, you know, most likely the most kind of mistakes that I will see probably from you guys is going to be little mistakes, right? Small errors where you maybe like miss this 2x, right? You take the derivative of, you just forget to use a chain rule there or something like that, you know, or you might miss like a negative sign or something like that. That's more typical. So I won't, like, especially on this test, the first like 1, maybe 2 minor errors like that where you miss a negative or something, I won't ding you for, okay? But if it's like, you know, gross errors, not gross as in yucky, but gross as in large errors, like you really mess up the product rule, really mess up the quotient rule, really mess up the chain rule, that will cost you points. But I won't, like, at least we're like, I'll give you like grace, like 1 or 2, you know, questions if you like just mess up like negatives or something like that. But, you know, then if you keep doing it over and over, then I will start dinging you for it, okay? So just so you know that too. Okay, so don't fret if you're like, Mr. Witt, you know, I can't be perfect on these. Well, we want you to be perfect eventually, but I understand we're still just learning them. So if you make like 1, maybe 2 small errors, I will let those slide. Okay, to start out at least. But later, won't be that case. All right. Next, what do you want me to do? Or other questions? Number 4. Okay. So let's see here. All right, I'm going to erase some of this here for number 7, so I can just give myself some more room for number 4. Okay. So number 4. Anyone see any helpful strategies here for us to use when we go to take this derivative? We're going to look at number 4. Any ideas about what to do here? To save us some headache, maybe? Make things a little easier? Yeah, okay, right. So, like, we can totally simplify this, right? I saw 3 of you guys light up there, so thank you. Yeah, 3 of you folks. Yeah, so we can divide by x, right? Okay, this thing is divisible by x. This thing also we can divide by x. We can totally rewrite this. Again, I'll just say this is like y equals here. We can totally rewrite this and say, oh, okay, this is x squared cosine x squared. By the way, when you see this, okay, the x squared is inside the cosine. All right, this is not saying, so this does not equal, let me write this. Okay, so when you see cosine x squared like that, it does not mean cosine of x squared, right? this is the same thing as cosine squared of x, right? You see the 2 here. And this is kind of a strange, like a quirk of our math notation that we use, right? Okay, this really means cosine of x squared there, just as a side note. All right, anyway, but yes, we can put that over x. We can also put the x tan 3x over x like that. And we can cancel out, cancel those out, cancel that x out with this x. And so we really just have y equals x cosine of x squared plus tangent of 3x. And man, does that make our life a lot easier, right? We eliminated that quotient rule. Okay, because if we didn't do that, oof, it would have been very messy. And again, you can take the derivative as it's currently written here, and it won't be wrong, right? You'll just make it a lot harder for yourself, that's all. Okay, it's much easier to take the derivative from here. All right, so when I go to take the derivative, what kind of rules are we going to use here to take the derivative of this mess right here? Let's just talk about this first piece. What kind of rules are we going to need to use to take the derivative of that first piece? Yes, it's a product. That's x times cosine x squared there, folks. That's a product rule, okay? What other rule? Also the chain rule, right? Because that cosine has an x squared inside of it. So this little simple, innocent looking little part of the problem here, that's a product and chain rule together. So again, we'll separate the two functions, right? They're the two functions. So I'll say the first times the derivative of the second. The derivative of cosine is negative sine. And then multiply by the derivative of what's inside, so times 2x. Okay, and then plus the second. Goodness gracious, I'm not going to have enough room here. Times the derivative of the first, so times the derivative of x, which is just 1. Okay, I'm going to move this over. Let's see. Make some room. Okay, then I'll take the derivative of the tangent of 3x, right? And what is the derivative of the tangent of 3x? Well, what's the derivative of tangent? What is the derivative of tangent? It is secant squared. So this would be secant squared of 3x. Okay, times 3 then, right? Times the derivative of what's inside there. And so again, you can stop right here and say, there's my answer. If you want to rewrite, you can, but you could just stop right here and say, okay, there it is, Mr. Witt. That is my answer. Please grade that. And I will give you full credit for something like that, okay? We could simplify just a little bit here. 2x squared sine of x squared plus cosine of x squared plus 3 secant squared 3x. So there's a little more simplifying, but not that much. Okay. All right. What else? Or any questions on that, or what else would you like me to do? Number 12. Find the equation of the tangent line. Ooh, okay. At the indicated points. So again, classic question that you'll see on the AP tests, stuff like that, right? Writing the equation of the tangent line. And so in order to write the equation of a line, right, what two pieces of information do we need? Yeah, a point and a slope, right? Do we have a point given to us here? Yes, we do, right? It's right here at 1, negative 2. So sometimes, right, they just say like at x equals 1. And then we have to like take that x equals 1 value. We have to plug it back into the original function here at the different, x's and evaluate to then get the matching y value. But they were kind to us here and they gave us the full point. So we don't have, that saves us some work, right? We already have the point, it's 1, negative 2. Now we also need to find the slope. And how do we find the slope of the tangent line? What does that require us to do? And once we take the derivative, then what? Yeah, we're going to plug in our point here, okay? And since, well, our derivative is only going to be in terms of x, yeah, we just need to plug in the 1. Actually, in the next lesson, we'll look at what is known as implicit differentiation, where the x's and y's are mixed together, right? Where we have functions, well, not necessarily functions, where we have, equations that we're going to derive or differentiate, where x's and y's are mixed together, and you'll see how that's going to, like, change things up a little bit, and we'll need to sometimes plug in a y coordinate here, plug in the y coordinate as well. But for right now, right, since it's the function is solved for y in terms of x, we just need to plug in that 1. So we'll get y prime equals, and then we'll just take the derivative here, right? So 3x squared minus. So taking the derivative of this is going to require what one of our rules? Yeah, chain rule. If you said product rule here, I would say, like, yeah, you're not wrong. But again, that 9 is just a coefficient, so we don't need to treat it like a product rule here. You totally can. Anything that has a coefficient, you could treat it like it's a product rule if you wanted to, but you're making it more complex than you need to. We already have another rule with coefficients, right? We just take the derivative of the function there. So anyway, derivative of cosines negative signs is actually going to become plus 9 times the sine of x squared minus 1. Okay, but yeah, we have that function inside we have to take the derivative of. So we'll multiply by 2x. Plus, and then, 6 to the x. The derivative of 6 to the x, that's that new derivative rule, okay, that showed up yesterday. The derivative of 6 to the x is 6 to the x times natural log of 6. Okay? I'm not going to lie here. It's going to be rare that you'll need to remember this derivative rule. So this is going to be one of those derivative rules that we know, right? But like we're not going to use it often enough that we're going to like remember it maybe as easily as some of the other ones, because it's not as common that we'll take the derivative of a number that's not e to the x, right? Most of the derivatives we'll have will be e to the x. Rarer will it be some other base other than e. Okay, so this is probably going to be a derivative rule that you might have difficulty remembering because it's used so rarely. But here it is, right, for our quiz. So anyway, now we'll plug in the 1. So okay, so what this becomes 3, and then 1 squared minus 1, that's going to be 0. Sine of 0 is 0, times 9 is 0, times 2 is still 0, so we'll just get a 0 there, right? And then 6 natural log of 6. Okay, so our slope, oddly enough, is 3 plus 6 ln 6. Okay, that's our slope. And so our equation, don't forget, right, we're writing the equation of the tangent line, so we're not done yet. We have to write the equation of the line. Y plus 2 equals our m, and please put parentheses around this, times x minus 1. And voila, there's the equation of your tangent line. Why did I put 6? It should be 3. Oh, I see what I did. Crazy, Mr. Wood. Sorry, it was 3 plus 6 natural log of 6. I miswrote it there, and so that must be up here. There we go. 3 plus 6 times natural log of 6 there. Okay, so there's the equation of our tangent line. All right. Other questions? Okay, I was like, I'm surprised that it took us this long to get to 13. I could have, swore. I was like really surprised that no one was like, Mr. Witt, 13, position velocity acceleration. I hate that stuff, right? So, yes, absolutely, I want to do 13. Okay, so a particle is moving along the x-axis, and its position for all time t greater than or equal to 1, that's kind of strange, is modeled by the equation x of t. So again, we shouldn't be too surprised that we're talking about the position of a particle moving along the x-axis that is described as x of t. right? So there's that. We're supposed to find the velocity and the acceleration functions. All right, so let's find the velocity first. How can we find the velocity given the information that we have in the directions up here, right? What do we do to find the velocity? Derivative of the position, exactly right. So velocity will be the derivative of the position, and thankfully it's nothing too crazy here. All right, it'll just be, you know, straight up 3t squared minus 6t minus 18. No strange, you know, no product rule, no quotient rule, no chain rule stuff. Okay, and then how do we find the acceleration function? Yep, derivative of velocity, or you can say the second derivative of the position, either one you want to say there. So yeah, a of t is equal to v prime of t, which is equal to x prime prime of t. And you don't need to write, you know, all this stuff that I'm writing here. You can just write a of t if you want to and just write it out. That's fine. I'm just writing it out for you guys for, like, you know, learning purposes and stuff like that too. But there would be 6t minus 6, right? All right, so far so good on letter A there. Velocity and acceleration functions. Okay. If you take the derivative of the acceleration function, there is a name for that. I forget what it's called, but it does have like an application and stuff like that, you know, in life, or, you know, in like some, you know, fields, like fields of science and stuff like that, but I forget what it's called. I think there is a name for it. Anyway, letter B. What is the velocity? Okay, so we're looking for a v of t, right? We're trying to solve for velocity here at the first time the particle is at the origin. At the first time the particle is at the origin. So how are we going to determine this? What should we do first here? We eventually want to find a velocity. But we have some other work that we need to do first here. And this is where the difficulties, in my opinion, where the difficulties position, velocity, acceleration problems come in, is interpreting the English into math, right? So where should we start here with letter B? I'm going to do this in a different color to try and contrast a little bit. Okay, so Sarah, what clued you in that it was the position that we want to set equal to 0 here? What about this sentence? Okay, so good. Yeah, I mean, if we are at the origin, that is talking about a position, right? When you are at a location, you are that's a position you're referring to, and so we should use the position function. And then you, how'd you know the position had to be equal to 0 though? Right, yeah, and so again, we're talking about the x-axis, right? So the x coordinate at the origin, right, is 0. So we're just going to literally set the position equal to 0 here, okay? So that's our first step, that's setting that position equal to 0. So t cubed minus 3t squared minus 18t equals 0. Okay, and now we're going to bring in some of our, you know, like pre-cal, algebra 2, algebra 1 skills here, factoring. So we'll take out a t, and we'll factor this quadratic here too. Would be minus 6t plus 3. Okay, so we'll get that t equals 0, t equals positive 6, and t equals negative 3. Okay, so we have 3 times when the position function there is equal to 0. But we're asked to find what is the velocity at the first time the particle is at the origin. Which one of these times is the first time the particle is at the origin? So why do you say 0? Okay, well, technically -3 is the smallest value, right? But why? Okay, so t is equal to time, so you want to throw out the -3 then, because it doesn't really make sense to talk about going backwards in time. Is that the idea? Okay, start at time 0. Well, that's a good question. What do the directions say about the time? Yeah, it starts for all time t greater than or equal to 1. So this 0, okay, this time 0, well, the particle's position is not modeled by this function for time values that are less than 1. Okay, so in this particular set of directions, right, and this set of directions was written this way, so that way we would have to throw out the t equals 0. Okay. Origin, Sam, does imply 0, 0, yes. But remember here, the origin, 0, 0, is a position. It's not a time, okay? The particle is moving along the x-axis. So the x-axis is going to give it a location, but the time that it's at the origin will be a different time necessary. It doesn't have to be at time 0. The particle is at position 0. The particle can be starting somewhere off the origin, right, and then moving left and right so that it gets to the origin eventually some later time. Okay, does that clarify for you, Sam? Or does that answer your question, I guess? Okay, perfect. Good question though. Again, this is kind of a bit of a weird kind of thing, right? So in other words, we must divorce in our mind. We have to divorce in our mind the idea that the x-axis is time. Okay, for this situation, right? We are told here the position of the particle moving along the x-axis. So the x-axis here is just its location on the x-axis, right? And time is a separate variable, okay, from this, okay? So we have to be careful with that because normally, yeah, time is the x-axis. Anywho, okay, so we've finally settled on that t equals 6 has to be our time here. And are we all okay with that? Any further questions about why it has to be t equals 6 there? Okay, so now what do we do? We're not done yet, right? I've identified the time, but what are we now supposed to do? Yeah. So again, don't miss the forest for the trees, right? What's the big picture here that we're trying to look for, right? What is the velocity at the first time? So we have that first time now. We still need to find that velocity. So we're going to plug 6 in. So it's v of 6 we want to find. So it'll be 3 times 6 squared minus 6 times 6, minus 18. Now, at this point, if it were not like multiple choice or something like that, this is all arithmetic, you could just circle your answer and say, Mr. Witt, this is the answer. And you would be right. You do not need to simplify arithmetic when you are writing out like free response kind of questions like this. Okay? So you can stop and say, done, that's my answer. And you can save yourself having to worry about, like simplifying arithmetic correctly and stuff like that. Okay? Or you can simplify it out if you want to. Also, another thing to keep in mind for these problems, just real briefly here before we continue on, when we're doing these kind of problems, keep an eye out for units, right? Sometimes they will say, in the second direction, after this set of directions, they'll say like, oh gosh, how did they say it? Well, anyway, please make sure you use correct units. Okay, if they give units, use those units. In this case, we're not given units, so you don't need to worry about telling me what the velocity is, what the units are here, right? They don't give us anything. But in general, if they give you units, you want to use those units because sometimes a point is attached to that. Okay, and you don't want to lose that point for something silly like not including your units. All right. Okay. All right. Letter C. What's the average velocity between 2, 4? Well, so again, I'll ask you a question, right? We do not have an average formula. We have an average rate of change formula, right? That's the slope formula. So if I want to find the average velocity, we don't have an average formula yet. We will later. We'll have a way to find the average velocity using the velocity. But right now, I need to think about velocity as the rate of change of something else, right? I need to rewrite velocity as the rate of change. What is velocity the rate of change of? Position. So I'm going to abbreviate here, rate of change of position. So what we're really going to do here, okay, and again, the common mistake the students will do here, they'll say, average velocity between 2 and 4, they'll say, v of 4 minus v of 2 over 4 minus 2. Okay, but that is not the correct formula here. Okay, because that formula that you just did, if you use that v of 4, I'll use a different color here too. Okay, that formula, this is for, this would actually give us an average acceleration here. Okay, so what we want to do is, again, rewrite the idea of velocity as the rate of change of position. And now we're really finding the average rate of change of the position. And we have an average rate of change formula. That is the slope formula. So it's going to be x of 4 minus x of 2 over 4 minus 2, like that. Okay, and then we'll just plug in the 4 there, and okay. I'm just going to use the arithmetic. So 4 minus 3 times 4 squared minus 18 times 4, and then minus the quantity 2 cubed minus 3 times 2 cubed minus 18 times 2, all over 2. Okay, and again, that's all arithmetic, so you could just circle your answer there and say, Mr. Witt, I'm done. There it is. Okay. No unit, so we don't need to worry about that either. Okay. All right, questions on that? So far, so good? I got 5 more minutes left here. Okay, perfect. All right, so we'll continue on. So then average acceleration, right? So let's use that same kind of idea, right? If we just talked about the average velocity, we really had to use the position, right? So for average acceleration, we're going to really use the what? Or acceleration is really the rate of change of the what? Yeah, velocity. Okay? And again, later we will develop a way, if we're asked to find the average acceleration, we'll develop a way to be able to use the acceleration to find the average acceleration. But we don't have that technique yet. It's going to require integration, which is coming out of a later unit. So right now, if we want to find the average acceleration, we have to use the average rate of change formula, which requires us to use velocity, since the acceleration is the rate of change of the velocity. Okay, so this would be v of 4 minus v of 2 over 4 minus 2. Okay, which would give us, let's see here, 4, gosh, maybe 6, and then 12 minus 12, so negative 18 over 2. I hope I did that math right. 4 squared, 16 times 3, 48. 4 times 6 is 24. 24 or 48 minus 24 is 24. Minus 18 is 6. Yeah, okay, that should be right. And so we end up with then, 24 over 2 or 12. But again, you don't need to simplify all this stuff. You could, again, just leave it, just like I did here. You could, like, leave it unsimplified and stuff like that, too. Your choice. Okay. All right, letter E, what is the position of the particle when the acceleration is 0? All right, so again, right, multi-step problem here. Where should we start, though, with this for letter E? Where should we start? Where should we start here with letter E? So when you say plug it in, do you mean like find A of 0, like that? There you go. Yeah, and I think I figured that's what you meant, but I just wanted to make sure that was what you meant. Yeah, so we want to know when the acceleration is 0, right? Is means equals, right? So we'll just set the acceleration equal to 0 here. So acceleration equals 0, so 6t minus 6 equals 0, so t equals 1. All right, we found when the acceleration is 0 at time 1, and that's part of our, our answers there, right? We can include 1, and then what do I do with that 1? Right, what is the position when the acceleration is 1? So the acceleration is 1 at time t equals 1, so now let's find that position. So we'll just do x of 1. Okay? Oh, nuts. Deleted too much. Man, the day, this thing's going crazy. There we go. And so that would just give us what? 1 minus 3 minus 18. So negative 20. Okay. And then finally, letter F here. Okay, and I think our class ends at 9. Our class ends at 9:50. Our next class ends at 10. So we can finish this last question for sure. Okay, and go again. If you got to go, go ahead. Please don't feel like you got to stick around too. Is a particle moving to the left or right when the acceleration is 12? Okay, so again, how should we start here? Yeah, right, when the acceleration is 12. So we'll set acceleration equal to 12, so 6t minus 6 equals 12. And so we'll get t equals 3. And so we have the time, right? We have the when the acceleration is 12 part. It's at time t equals 3. Plug that into velocity. Exactly right, Basil, because remember, velocity, right, it indicates not only our rate of change of position, right, how fast we're going, right, like your speed, but in addition to the speed, it gives a direction. So we're going to plug that 3 into the velocity. And let's see, it's going to be 3 times 3 squared minus 6 times 3 minus 18. Okay, so we plugged it into the velocity, and then what are we looking for here? Once I plug that into the velocity, what am I looking for to determine the direction this particle is moving? Positive or negative, exactly right. So 3 squared is 9, times 3 is 27, and then minus 18 minus 18. Okay, so we can see here we're going to be less than 0, right? It's going to be, what, a negative 9? If I do that correctly, right? Is that 36? Yeah. Yep. Okay, so negative 9. So left or right? Yeah, left, because, and again, you don't have to give a justification here, but I'm going to give a justification just so you guys can also see that, because sometimes you'll be asked to justify your answer, because A of t equals 12 when t equals 3, and V of 3 is less than 0. Okay, so you feel free, feel free to use those like math symbols, right? Legitimate math symbols in your justifications if you have to justify something. All right. All right, and there's that. All right. I don't have a Block 2 class, so I am happy to continue staying on this video if you guys want to, and continue to ask questions up until your class or even into your Block 2 class. That's your decision whether you want to be late to your Block 2 class, or maybe you don't have a Block 2 class you have to go to or something. I'm happy to stick with this and continue to answer questions if you would like. Okay, so you guys stick with me as long as you want, and as long as whenever the last person leaves, then I will stop the video, and of course I can also see you in office hours and things too. Okay, so if you guys want to stick around, please continue to ask me questions. What else would you like to see? I have planning right now, so I don't have a Block 2 class, so I can stick around for as long as you guys want me to. I mean, until set, obviously, then I have to go. But yeah, I'll be happy to answer any questions if you want. Yep, 12:30 to 3:30. Show up. OHS WID support. Okay, if you're going to do that, okay, I can maybe do that. Yeah, I'll stay in this meet then. for that. So if you guys want to come see me during your Block 2 class or something, you finish early, I'll be here as well. Oh, I hear you. Well, okay. Can you make it to office hours, you think? Okay. Then just show up for that maybe, and we'll see. Because we have some other calculus folks that are going to need some help too. All right. All right. Yep, see you, Gavin. Take it easy, guys.